Okay, let's take a look at a quadratics question. Hopefully not too bad, taken from an exam. So here you've got a quadratic. The variable of the quadratic is x, but there is a constant k which forms part of the coefficients, specifically two of the coefficients. Your question then is, can you find the k, or let me go back on that slightly, can you find the conditions which k must satisfy in order for this quadratic to have two distinct and real solutions? So you have to think of, how do I mathematically express what this is saying? Two distinct real solutions for x. Once you've written an expression which lines up with that, then that expression will hopefully be able to be reduced to this expression here. Okay, so that's what you're doing in part A. And for part B, going on from part A, can you then find the set of possible values for k? Okay, so give that a go. Pause the video now. Okay, so we need to show that k satisfies this constraint. In order to do that, let's go back to what was the equation. So it's k plus 3x squared and 6x plus k, and that's equal to 5. Okay, so it's not quite in a standard quadratic form yet because it's equal to 5 rather than being equal to 0. So what we should do really is multiply this out and see if we can get this into a standard form. In fact, no, we don't have to multiply much out, do we? We just need to move that 5 across. So, sorry, forget what I said. Don't multiply out. Keep the coefficients of x squared and x, but then our x to the 0 coefficient, effectively our constant, that's k minus 5. Okay, so we got this, and I'm going to put this in brackets. So in terms of quadratics, this is effectively my a coefficient, this 6 is my b, and this k minus 5 is my c. And as we know, to have two real solutions to a quadratic, that must mean that the discriminant, b squared minus 4ac, must be greater than or equal to 0 in order for them to be two real solutions. And in fact, this square root we don't need because square root of 0 is 0. So really, this is the condition we want. B squared minus 4ac is greater than or equal to 0. However, they need to be distinct. So they can't be the same value. You know, because sometimes in a quadratic you have duplicated roots. And being distinct, that therefore means we only want greater than 0. We don't want to include the equal sign. Okay, so let's find out what that is then. B squared minus 4ac. In this case, b is 6, so we've got 36 for b squared, minus 4a times c. So that's our a, that's our c. And the condition is that all of that needs to be greater than or equal to, greater than 0. Okay, let's get rid of all that. And now is the multiplying out. So let's see what we get. I'm always a bit slow with these things. Let's see. 4k squared. Okay. All right, almost done. And I'm going to multiply everything through by minus 1 and simultaneously collect a few things. So that 20k minus 12k is 8k times the minus 1 is minus 8k. Here I've got minus 60 greater than 0. Let me just make some space. Okay. In fact, something I probably could have done earlier, but I'll do it now, is to just divide by 4, because that actually divides cleanly into all of the coefficients we've got there. 96 divided by 4, 24, isn't it? Oh, and one thing, I should have pointed this out at some point. Obviously, I multiplied by -1, and at the moment I did that, what I should have done is immediately flipped the sign of the inequality. So you can see I rushed that a little bit. Remember, you need to flip the sign if you multiply by -1. Okay, cool. All right, and then that, yeah, that is in fact the answer we were looking for. K squared minus 2k minus 24 is less than 0, and that results directly from considering the discriminant. Let's look at part B. Okay, so we're going to find the possible values of k. In order to do that, let me just bring across then what we determined in the previous section. K squared minus 2k minus 24 is less than 0. Right, so you've probably guessed we want to factorize this. Guessed is probably not the right word. You've probably deduced that that's what you have to do. What have we got? K minus 6 times k plus 4 should work. Yeah, is less than 0. And at this point, you may have been taught various ways to do this. I always like to consider the graph, because the graph, you know, you can't really go wrong with, well, you can go wrong, but if you've drawn the graph correctly, then, you know, your intuition can sort of play its role a lot more easily. So this graph is going to cross at 6 and at -4. It's a k squared graph, not a minus k squared graph, so therefore it's a U shape. That's all we really need to know, really. Don't particularly care where the minimum is. You know, perhaps I've drawn it wrong, perhaps I've drawn it right. It doesn't really matter. It's a U shape, and it passes through -4 and 6. And that then tells me that, okay, if I want to know when this thing's less than 0, well, it's less than 0 in this area, isn't it? It's less than 0 there. Okay, less than 0 meaning the y coordinate of every point on that yellow curve is less than 0. So therefore, you know, I'm interested in the x values corresponding to, you know, this range here that I've highlighted in red. This is the range of points for which the output of the graph has a y coordinate of less than 0. So what k coordinate does that correspond to? If I can call it a k coordinate, I suppose it's the next coordinate, but what k value does that correspond to? Anything between -4 and 6, right? So here we've got when k is less than 6 or bigger than -4, then the output of this function is in fact less than 0, and the output is the y value. So therefore, we can say for our final answer, we're going to say k is less than 6 and it's greater than -4. And we're not going to say less than or equal to in either case, because here we also do not include 0. So therefore we don't include the points themselves, the -4 and the 6. Cool.